We live on a blue planet, but that color is deceiving. While oceans cover most of the globe, the amount of that liquid we can actually use to drink, grow crops, or power our cities is a tiny fraction of the total. This diagram shows the true scale of water on Earth. 97% is saltwater. Of the remaining 3% that is fresh, the vast majority is locked up in glaciers or buried deep underground. Humans rely on a minute fraction, about 1% of surface freshwater, to sustain almost all industrial and biological activity. This map highlights projected global water availability. By 2025, over 30 countries are projected to have water levels below 1,000 cubic meters per person per year. The resource simply isn't located where the human populations are growing. When water does arrive in nature, it is often destructive. Unmanaged rivers can transform into violent torrents that overwhelm natural banks, destroy housing, and wash away fertile topsoil in a matter of hours. Surviving this geographical mismatch requires moving away from relying on nature's erratic cycles. We have to apply the rigorous, mathematical discipline of hydraulic engineering to physically rewire how water moves across the land. Planning hydraulic resources begins with identifying local problems and measurable objectives. Engineers compile exhaustive data, measuring basin hydrology, bedrock stability, and soil capacity to establish water availability versus demand. This data feeds models to formulate alternative plans and risk analyses, driving the final decision. The math includes socioeconomic factors. Local demographics, economic growth rates, and community organization dictate the specific infrastructure a region can actually afford and sustain over its life cycle. The physical dams and spillways are the end result of this massive, invisible, data-driven planning phase. Because this planning phase is so intensive, modern megastructures are designed as multi-purpose projects. This means a single infrastructure network is built to solve several different societal needs at once. This schematic of Peru's Chinacas project maps out how this works in practice. Engineers trace a deliberate path, diverting water from the river through a network of canals and tunnels that stretch across the geography to reach specific population centers. The first objective is transforming the landscape. Routing controlled water into arid zones creates a sharp division where barren desert becomes high-yield agricultural ground. The second purpose captures kinetic energy. Descending water is forced through massive hydroelectric turbine structures, generating electricity to power the entire region. Simultaneously, reservoirs at the top of the system laminate extreme floodwaters to protect downstream towns, safely siphoning off a supply for consumption. A meticulously planned megastructure acts as a central engine, driving agricultural production, fueling industrial growth, and ensuring residential survival. To execute these plans, the physical hardware required is massive. Building a dam involves anchoring thousands of tons of concrete and steel into the walls of a mountainous valley to hold back millions of cubic meters of water. Moving that resource requires heavy machinery to lay the massive concrete aqueducts, siphons, and pipelines that carry the high-pressure flow from the reservoir out into society. The engineering job continues long after construction. This infrastructure sits within a dynamic natural environment. It requires constant daily operation to balance demands, clear sediment, and monitor ecological shifts. Maintaining these networks requires permanent staffing to monitor flow rates and structural integrity, ensuring the system survives the natural environment it was built to tame. This diagram traces the final leg of that journey. The resource is pumped from a source, filtered through treatment tanks, and pushed through a final distribution grid directly into a home, pressurized for the end user. We started with an unpredictable, chaotic force of nature. Now we have a heavily regulated system, capable of a controlled release of thousands of gallons a second without washing away the valley below. Every reliable liter of water reaching a home is the outcome of a coordinated engineering effort, one that turns a chaotic environmental threat into a predictable and life-sustaining utility.